will come. Okay, so welcome everybody to this new seminar of the official IAU G2 online conference series. This is about massive stars, and today we have a different special seminar. This is not exactly by an early career researcher. She's quite experienced already, and the motivation of this seminar is that I learned that Miriam Garcia, who will be the speaker today, delivered a very interesting and nice seminar a few weeks or months ago in the Space Telescope Science Institute related to, or in the framework of the Ulysses workshop. So this talk was about perspective, future perspective on massive stars related to instrument developments. And as commonly happening nowadays, she didn't have enough time to present things properly. So then I thought that could be a very interesting thing if she was giving the longer talk or longer version of her talk, because it's something that I consider is of interest for the broad community. So today will be about next generation observatories and prospects for massive stars. But before, I want to make a brief introduction of Miriam's career. She's presently staff researcher Centro de Astrobiología in Madrid, and all started more or less in 2099 or so, and she defended her PhD in 2005 in the Universidad La Laguna, but she actually developed most of her PhD in the Johns Hopkins University in Baltimore, and she had a supervisor, Artemio Herrera and Luciana Bianchi. After that, she was awarded several postdocs at the Instituto de Astrofísica Canarias and also the Centro de Astrobiología until she won the permanent position in 2021. I wanted to highlight here a few research achievements she had during her career. She started doing UV spectroscopic analysis of massive stars to try to decipher stellar information about massive stars using IAU Fuse and HST, and also using the VM Basic Stellar Atmosphere Code developed by our colleague Adi Poldrack. And soon after the PhD, she decided to move a bit, still in massive stars, to something more groundbreaking, going to study massive stars in very metal-poor galaxies, meaning metallicity lower than the SNC. And for that, she had to start using large telescope and combine photometric techniques for the identification of candidates that were known, and then spectroscopy to obtain information about the physical properties. And as an example, I can quote a couple of works she did with her PhD students, Inés Camacho and Marta Lorenzo, on sextant A, that is 1/10 solar metallicity, but there are other galaxies that are also interested in their gas. And I want to also highlight that she has been very active in the last decade in the coordination of future strategies and new instrumentation of interest for pushing frontiers of massive star research towards the condition of the early universe. And this is why I think she's very well fitted to deliver this talk for the community. And especially I want to highlight her participation in the instrument definition and design of LUVOIR, the ultraviolet multi-object spectrograph that could go to in LUVOIR, and also the coordination and implementation of a white paper submitted to the ESA Voyage 2050 survey, proposing a 10-meter class observatory in space to bring UV and optical. She has many other interesting achievements, but I'm going to stop here because if not, this will be too long. But I wanted to highlight that she has been awarded more than 200 hours of observing times in the largest telescopes in the world, including both ground-based and space, GTC, VLT, JWEB, HST, SAL. So I think it's going to be a very interesting talk with Miriam telling us about what is her vision about what is the future on massive stars related to stars closer to the early epochs of the universe. So thank you very much, Miriam, for accepting our invitation.
Well, thanks very much for this very flattering introduction. It does sound like something, but yeah, I'm just very interested in these very metal poor stars, and because current instrumentation is not enough, this is how I became involved with with as many future instrumentation as I can. And this is a little bit why I am delivering this talk today. So let's begin. Past the formalities of acknowledging my grants, I would like to thank, I would like to thank a bunch of people who either got me involved into these instrumental projects, or they have taught me a lot of things, or they have provided material for this talk. So thank you all very much. I'm sure I'm forgetting something, so please forgive me if that's the case. This is going to be the outline of the talk. So first, I'm going to talk about what future instrumentation is on the table. And I have to say that this is a little biased by the projects and the observatories that I'm involved in. So I'm sure if I forget your favorite instrument, please forgive me. I would be happy to know about it, either at the question sessions or offline. And in the second part, I will overview a number of open questions which may be driving at least partly the design of these new instruments, because these are usually very, very big projects, and one science case is not enough. So usually there are very big consortia reaching galaxy people, star people, planet people, cosmology, and together we put together all the exciting things that we need to learn about. And that's what finally gets us the funding for the instrument. So let's begin. So the James Webb Space Telescope is already in space, and a few years after it launched, it was time to think about what the next big project was going to be. Many of us were very excited to think about the real, truly Hubble Space Telescope successful. Because James Webb is very nice, can reach galaxies at the dawn of the universe, which obviously is impressive. But for people like us who do stellar astrophysics, it's really not so helpful. So some years ago, there was this call, I think it was the US Academy of Science, for ideas of new concept studies for this new flagship telescope. And as far as I know, there were 4 concepts with teams gathered around them. And I became involved in LUVOIR, the Large Ultraviolet and Optical Infrared Surveyor. So LUVOIR used to have, well, I don't know why we give it the French touch when we pronounce it, because really it doesn't have to do anything with France, but it sounds good. LUVOIR had 2 designs with 2 different mirrors. So we are scientists, of course, we always want the biggest, the largest, the better. And we were rooting for a 15-meter diameter telescope in space with capabilities, like I said, in the ultraviolet, the optical, and the infrared. And these were the 4 instruments that were proposed. Eclipse, which was an extreme coronagraph to be able to detect planets with direct imaging. The high definition imager, which was the wider field camera. LUMOS, which would have been the ultraviolet spectrograph. And for the first time, we would have had multi-object capabilities in space. And Pollux, which was the European contribution, and I will get back to Pollux later on. So these concepts were submitted to the Astro 2020 Decadal Survey, together with a bunch of papers that we scientists submitted, pointing out what we thought the most urgent questions in our respective fields were. This was analyzed and studied by the committee of experts that the Academy put together. And this is a summary of the results. The report is very extended, but in this figure, they summarized the technological and the instrumental recommendations for the next decade. And one of the early, sorry, my mouse is acting funny, okay. One of the first recommendations was this flagship for infrared, optical, and UV spectroscopy. So we were all very happy about it. After some years, after some months, this translated into what we now know the Habitable Worlds Observatory. And which is largely based in the concepts of both the LUVOIR and another concept, HABEX. And the main goal is to detect one planet like Earth and characterize the atmosphere and look for biosignatures, but being able to see the planet with direct imaging. So I'm going to stop this because anyway, I don't think you can see it very well. So at the moment, everything is basically to be determined, but it seems that it's going to have an 8-meter circumscribing diameter. We were a bit worried at the beginning because the recommendation was 6, but this is the inner diameter of the telescope, sorry. But the outer one would be more like 8 meters. And the design is going to be very similar to LUVOIR B. LUVOIR B was the second design for LUVOIR with a smaller diameter, and it is off-axis. Like I said, we don't know instrumentation yet. At the moment, the teams are being assembled to gather experts in different fields to, again, distill what the most important questions are, so that these questions and the technical specifications they need for the observations can drive the technological development and the final definition of the instrument and the observatory. But as far as I know, the diameter of the telescope is still open, the final instrumentation is still open. There are 3 instruments that apparently are going to be on board, which again are the coronagraph, the imager, and the multi-object ultraviolet spectrograph. But at the moment, the scientific teams, we have been given the freedom to just propose whatever we think it's really needed to answer the questions we need to answer. So if you see this list of instruments, Pollux is no longer here. So I'm going to talk a little bit about Pollux. Pollux was going to be the European contribution to LUVOIR. It's a very high resolution spectrograph and a spectropolarimeter that would work from 900 angstroms to 4,000 angstroms. And at the moment, the consortium around Pollux is still active. The design of the instrument has been reviewed to fit into Pollux B, but we have a couple of hiccups. One of them is that the off-axis architecture of hub worlds implies that we have more reflection, and this is not good for polarimetry, although the simulations are very optimistic in that we can get rid of that with some calibrations. And the second and most urgent problem is that we don't know if there is room for Pollux B in the Habitable Worlds Observatory. But I'm taking the opportunity of this slide to explain that in Europe there is a big interest about the spectropolarimetry, and in fact there are 2 other mission concepts that have been proposed in different calls for ESA, for the European Space Agency. And one of them is EUVO, the European Ultraviolet and Visible Observatory. That would be a telescope with 6 to 10 meter diameter, so pretty large aperture, with again very high spectroscopic resolution, very high resolution spectropolarimeter, again working from 900 to 4,000 angstroms. And the ultraviolet spectrograph was considering also multi-object capabilities, and maybe, and this is new in space, the possibility of sending an IFU, an integral field unit. And the last mission I want to talk about is Arago. This is a smaller telescope with 1 meter diameter, and we have proposed this as a candidate for a medium-sized mission from ESA. It has not been successful yet. And again, it's high, not so high, but high spectroscopic resolution in the UV all the way to 9,000 angstroms. And we needed to make a trade-off. If the collecting power is not so big, then resolution cannot be so high if we need a high sigma to noise ratio. Okay, so, well, and there were some similar developments for spectropolarimeters in the US. So I will argue afterwards in the talk that continued access to the ultraviolet range is very, very important for massive stars, mostly because this is the best place to study radiation-driven winds, or one of the best places. And we need to be aware that Hubble Space Telescope is still working well, but it's not going to be there forever. And at some point it will shut down, and there will likely be a gap between HST and Hubble worlds. And one possibility for continued access in the ultraviolet is this World Space Ultraviolet Observatory. This is a Russian-led mission. Spain is involved with the focal camera unit, which is basically the camera, but also there is an additional instrumentation, like very high resolution spectroscopy, and UV specs, which would be a contribution from the Japanese agency to study Lyman alpha and this neutral oxygen line in stars that host planets. So this would be a very interesting solution to have this continued access to the ultraviolet range. But like I said, this mission is led by Russia, and we are all aware of the situation. So we don't know if or when this mission is going to launch. So that's for space, but we Europeans are also very excited about the European Extremely Large Telescope. This is going to be a 39-meter fragmented telescope with more than 800, made out of almost 800 mirrors. And I found this was very curious. The factor limiting the size of the primary was actually the size of the secondary mirror that needs to be monolithic and can only have a maximum of 4.2 diameter. So this is actually what drove the final size of the ELT. And the expected first light is going to be 2028. This is a summary of the first light instrumentation. The first instrument that will arrive will be Mikado. Mikado is the wide field imager working in the infrared and also in the I and the Z bands. It will have a coronagraph. It will work with two different field of views depending on the plate scale that we want. If we want to have higher spatial resolution, then the field of view will be smaller. And it will offer the possibility of doing single object spectroscopy at resolution of 2000. This instrument will arrive in 2028, and it will be used to do the commissioning of the ELT. The second instrument will be METIS, which is the mid-infrared camera that works in the L, M, and N band. That's 3 microns to 13 microns. Again, this is the field of view with the plate scale. It also offers low resolution spectroscopy in the L and M bands and very high spectral resolution spectroscopy with an IFU, which will be coupled with a coronagraph. So I guess this will used a lot to study planets. This instrument will arrive in 2029. Then in 2030, the Morpheo will be in the telescope. Morpheo is the instrument that serves the adaptive optics. So this means that until 2031, the ELT will not have any adaptive optics. So it's like having the big telescope without the glasses. So once the IAU is working, the first instrument will arrive, which is Harmony. Harmony is quite a small integral field unit spectrograph, but it has exquisite spatial resolution. Again, it can work in several spatial resolution modes, depending on the plate scale we want to use. And the technical specifications are still not closed. For sure, it will have an infrared channel covering the J, the H, and the K bands with low, medium, and high spectral resolution. And some of us are fighting to keep there an optical channel that would go all the way down to 4,500 angstrom, something like MUSE. So this is the first line instrumentation. These instruments are fully funded by ESO, but the 1.5 generation is already in the planning. One of these instruments is Andes, which is a very high spectroscopic resolution spectrograph. It would be a resolution of 100,000 with the possibility of having an IFU. And so it's like multiplying the possibilities of a spectral resolution by a lot. And the other instrument is Mosaic. And here, what they want to potentiate is the field of view. So it's going to be an extremely wide field of view spectrograph with 7.5, this should be minutes, sorry, no arc minutes, 7.5 minute diameter, and some IFUs. It will work from 4,500 all the way to the H band, a little past the H band. Again, the technical specifications are not closed. So a bunch of us, again, are trying that the spectrograph reaches all the way down to 3,900. And the resolution would be basically 4,000. We might push this a little bit higher with some selected spectral windows of a resolution of 18,000. And the power of Mosaic is that it will be able to study simultaneously 200 objects. This is not the only wide field spectrograph that's on the planning. What I'm going to show now is very preliminary and is some information about the wide field spectroscopic telescope. This will be a 12-meter telescope devoted exclusively for spectroscopic surveys. And it will have a humongous field of view of 3.1 square degrees. And this would be covered with, very likely with fibers. And the part that is more interesting to me is the central IFU. So it will be a combination of both. You have the IFU in the middle and then all the positioners around the central IFU. So this is what it's, sorry. This is, wait, let me, okay. Sergio, can you see my mouse?
Yes, we can.
Yeah, because it's more, it moves faster than the pointer. So yeah, so this would be the 3 square arc minute field of view. And for comparison, this is the field of view of MUSE. And the idea would be to collect a spectra of many objects. It could be up to 20,000. And with resolution of 4,000 to 40,000. Of course, if you observe many objects, you cannot observe, you cannot use the highest if you want very high spectral resolution, then you will need to go for the lower multiplexing just because you don't have enough room in the detector to collect all the spectrum. But like I said, this is very preliminary. At the moment, we have just submitted the white papers proposing the science that would support the construction of this telescope. Nonetheless, it's pretty interesting to our science, I think. Okay, so I mentioned here MUSE. MUSE is, I'm not sure if it's the widest field IFU that we have at the moment, but for sure it is the one that provides the best trade-off between the field of view, which is 1 square minute, and spatial resolution, because it's AO assisted and it's really, really nice. This is the best instrument we can have to build the population of massive stars in other galaxies. And because MUSE is working so well, there is a team also thinking of the successor of MUSE, which would be Blue MUSE. And it would have a couple of very interesting advantages. The first one would be the spectral coverage. This is the spectral coverage of MUSE, which begins at 4,600 angstroms. As you know, this is not optimal for massive stars. But Blue MUSE would cover from 3,500 angstroms to almost 6,000 angstroms. Okay, it leaves out H alpha, but we have the 4,000 to 5,000 spectral range cover. And we would have it with a bit larger resolution than MUSE. MUSE is only resolution of 2,000 and Blue MUSE would be 3,500. And also they are increasing a little bit the field of view. And this instrument is ongoing. It entered ESO's phase A early this year. So let's hope we can have it in the telescope soon. Okay, so I think this is it for instrumentation. I don't. If there is any question that cannot wait, maybe this is the moment to make it. Otherwise, I will continue with the next section. No, okay. So the next section is about exciting questions we need to answer about massive stars. So let me pull up this schematic view of the evolution of the universe from the Big Bang until today. And this is a very grateful audience. We are all massive stars, so I don't need to emphasize this, but massive stars have been there from the very beginning, from the very first stars that some simulations say that could be 1,000 or even 10,000 solar masses. That's up for debate in some other forum. They also provided the photons needed for reionization of the universe. But ever since, in all the galaxies that are forming stars, massive stars have been injecting kinetic energy, ionizing photons, and they have released the material process in their interior, thus enhancing nucleosynthesis. But not only that, massive stars are also probes of the universe. Their spectrum dominates the unresolved spectra of star-forming galaxies, like the one I show here, but also they are progenitors to supernovae, kilonovae, superluminous supernovae, GRBs that are so bright that can be used to probe star formation up to very high redshifts. And also there are some outstanding open questions that have massive stars at the core. Like for instance, these observations that James Webb is taking of galaxies at very, very high redshift that already show a non-negligible enrichment of some chemical elements. We know that massive stars are related to massive double black holes, but we still don't know yet how they can be formed. There is very narrow helium-2 nebular emission detected in some galaxies, and we still don't know what exciting stars could be. Like they are likely massive stars, but we don't know for sure. So to understand all these many phenomena in the universe, to understand what's the feedback of massive stars, and to use massive stars as tools to interpret the universe, we need to understand very well how they live, evolve, and die. And as you all know, we don't know yet. And that's and I think I've grouped the questions in 5 different sections that I'm going to cover now. So the first one is radiation-driven winds, propelled by the absorption of photons, absorption and re-emission of photons by metallic lines. Radiation-driven winds can remove sufficient mass from the star as to change the evolutionary track in the HR diagram, and also to change the final end, a supernova explosion. So this is something that we really, really need to know very well how they work. And these are also the reason why we need continued access to the ultraviolet range, because as I show here, there is a wealth of diagnostics for the wind that we do not have in the optical or in the infrared ranges. But maybe Joe can say many more, and many of you can say many more of this. We don't know well yet how radiation-driven winds work. So ever since the Castor-Abbott claimed theoretical framework, we know that the mass loss due to the wind should increase with increasing luminosity, because there are more photons that can propel the wind. And also the mass loss rate should increase with increasing metallicity, because there are more metals in the wind that can absorb this energy and this momentum. And overall speaking, everything works well. But devil is in the details, as they say, and things are not as good as they look. So we don't know if there's a stability jump yet. This is a change of the mass loss that could exist or could not, but initially was thought to be due to the change of the ionization equilibrium of iron, which is one of the main carriers of the wind. I forgot. I thought I have forgotten a paper, but no, I think they are all here. There's a strong debate at the moment going on with this. This relationship between the luminosity of the star and the momentum of the wind does not always behave well. We have many exceptions, most notably at the low luminosity regime, where some stars register weak winds, and also in the high luminosity end, where there could be a kink. And the metallicity dependence of radiation-driven winds have only been tested all the way down to the metallicity of the small Magellanic Clouds. The reason, as I will argue afterwards, is that we don't have many more stars with poor metallicity. There is also the issue of inhomogeneities in the wind that affect the derived mass loss. We don't know if the inhomogeneities are optically thick, optically thin, both, how this is entangled with the velocity field. And of course, and computer power permitting, we should really start thinking about this, about 3D winds, 3D effects in the wind. So in this Ulysses workshop, John Sundquist showed some very, very amazing simulations. So basically, if you consider the 3 dimensions of the wind, you don't need to take into account parameters like macro turbulence. They come naturally with the description of the wind. So I think we should expect big results from this line in the near future. But anyway, the take-home message is that there's many open questions on radiation-driven winds, and the best place to answer them is the ultraviolet. And for that, we will need either hub worlds or a mission like the World Space Observatory. I wanted to speak just very briefly about narrow absorption components, which are these tiny absorptions we see in very high spectroscopic resolution on P-Cygni profiles. And if we do a time series of stars, they seem to be migrating toward higher velocities until they reach the asymptotic value of the terminal velocity. But we don't know what the origin of these NACs. It could be co-rotating interaction regions. I think there's also a paper by Alexander David Urath where he included some magnetic hotspots in the wind. He could also reproduce the NACs. And this is something that could tell us information about the geometry of the wind, or at least the very near circumstellar region. And for this, And to be able to track the evolution of NUCs, we will need very high spectrographs, very high resolution spectrographs, coupled with a very wide aperture. So we can take very high signal to noise ratio spectra very fast in order to track the evolution of these features in very short timescales. Okay, the second group of questions is binary systems. So as the older people in the audience know, we've been trying to look the other way with respect to binaries for many years. This was something that bothered our observations, but a couple of recent results, well, not so recent anymore, made us confront the reality that we needed to take binaries into account. And the first one was the realization of the high fraction of binaries within massive stars, and that 70 of those binaries will interact with their companion throughout their life. So, of course, we need to understand single object evolution. This is a very basic, but once we have that under control, we need to understand what the interactions with the companion are going to be. And the second result, of course, is the observations by gravitational waves observatories, with the very first merger detected, showing that we had a black hole with 30 solar masses of each component, and our model just could not produce such high mass solar black holes. And ever since, now we see binaries everywhere in the HR diagram. So where's my mouse? Yeah. So blue stragglers, red stragglers that in this HR diagram are not present, but are seen in other clusters. High mass red supergiants, luminous blue variables, some blue supergiants. Many of these are either the product of a binary interaction or directly, or we think that they could be directly mergers. So we need to understand how many of these are related to binary, and we need to reinterpret the HR diagram. So this is one possible schematic channel for the evolution of one binary system. I'm not gonna get into detail for this one, but I wanted to highlight here two things. One is the many stages with very characteristic observables that we need to map in the HR diagram. And the other thing I wanted to highlight is that one of the phases that we may find very often is a star that has been stripped of its outer layers, or at least partially stripped, and therefore we are left with a more compact core, which is very, very warm. And it's very important to detect these companions. In this specific channel of evolution, this stripped star would take the shape of a warm-fire star, but it could be, it doesn't need to be extreme, and it doesn't need to know wind features. And they could be hidden. And that's what I show here. So here I show the composite spectrum of one of these stripped stars and their companion. And in the optical range, you would basically see nothing weird, except perhaps for this helium-2 emission, that if you work with very low signal to noise ratio spectra like myself, you will think that maybe this is noise or whatever. But in the ultraviolet range, if this stripped star is really hot, maybe it would have shined the other companion. And that's what I show here. And it's very important to detect these and other similar companions, because otherwise we may be led to wrong results. So for instance, I quote here papers that reported black holes. The first one was special because it was initially thought to be a 70 solar mass black hole. And the second one was special because it would have been the closer black hole to Earth. But once the spectra were analyzed into detail, these were broken down into a strip P star and a BE accretor. So we really need to look for these hidden companions. And the ultraviolet could be the best place to look for them. So here, for instance, I highlight the work by Lee Patrick. So basically, they are looking for companions of red supergiants by studying the excess in the ultraviolet that would be produced by the strip companion. And with photometry, they are even able to, of course, they have the mass of the red supergiant, but they have been able to infer the mass of the binary companion, of the strip companion. And a similar work has been done by Maria Draut and Ivan Gottberg. And basically, they look for candidate system to host this strip companion by looking for stars in this area of the color magnitude diagram. So in this color magnitude diagram, the x-axis is a UV color minus a V-band color, and the y-axis is the ultraviolet. So everything that is hotter than the sums, and it would be here, there are candidate system to be hosting a companion. And of course, if this companion is detectable in the ultraviolet, if we take ultraviolet spectroscopy, we would be able to determine its characteristics. So again, this is a case for a wide field telescope in space with ultraviolet capabilities. And if the diameter is big and the sensitivity is good enough, I think HubWorlds is going to provide very deep insights into the statistics of binaries that are really going to help us understand the massive binary evolution. Okay, so magnetic fields. Magnetic fields is, again, another area where a bunch of us have been looking the other way because it just makes it very complicated to understand the evolution of the star. But thankfully, there have been big surveys like MIMES, Bob, and Dynamics that have tackled the problem and have shed some light, at least into the statistics of the magnetic fields. So thanks to these surveys, now we know that the frequency of magnetic fields is about 10%. We believe that the origin is fossil. This means that the magnetic field is inherited from the cloud where the star formed, although it could also form by binary interactions or mergers. The fields are not very strong, few kilogauss at most, although usually it's 10 to 100 gauss. It's dipolar, and there is no clear correlation with the stellar properties except for rotation. So one may think, okay, a frequency of 10%, that's not so much. But in reality, we don't know what happens with the other 90%. So maybe they have very weak fields that have not been detected. And moreover, we know very little about what happens in the post-main sequence stages. And of course, it's very hard to study magnetic fields in the Milky Way. So imagine going to the Magellanic Clouds. So at the moment, we have very few insights on what's the metallicity dependence on the evolution of these magnetic fields. And the thing is that the impact of magnetic fields in the life of the star is important. So in the stellar interior, the magnetic field interacts with the angular momentum transport mechanisms, and it can break the star, it can decrease or even stop the rotation. In the atmospheres, the magnetic field interacts with the wind. If the wind is strong, it can be locked in the magnetic loops. That means that a significant fraction could fall back into the star. And that means shocks, of course, but most importantly, we could decrease the mass loss rate. And there are very interesting papers demonstrating that we could achieve 25 solar mass black holes at solar metallicities that at the moment that previously we thought it was impossible if magnetic field is present. And the magnetic field is also going to change the evolution. So this is a summary of a very interesting work by Salt. The team tried two different magnetic field topologies and studied how it interacted with two internal angular momentum transport mechanisms. And what they show is that the evolutionary tracks can change and that the surface abundances are going to change as well. And finally, and I finish with magnetic fields, we know that massive stars are progenitors to magnetars, pulsars, neutron stars with strong magnetic fields. So we need to know if these magnetic fields survive the evolution of the star, or if this is a new magnetic field that is developed at the time of the supernova explosion. And I think at the moment there are not enough observational constraints. So for that, we need to understand magnetic fields. Magnetic fields can be studied either with the spectropolarimetric part of the Zeeman splitting, or also with the Hanle effects. And of course, we also have the OFP stars, but those are an exception. So basically, what this means is that we need to study many photospheric lines, and for that, and we need very high spectral resolution with very high signal-to-noise ratio. And for that, the ultraviolet is optimal to study the magnetic fields because it's the part of the electromagnetic spectrum where we have more photospheric lines. So we need to constrain the Stokes parameters, build surface intensity maps, and hopefully with least square deconvolution technique, build the magnetic field topologies. So for this, again, an instrument like Pollux on Hub worlds or like UO will be fundamental to study the magnetic fields. And this is one of the reasons why the European community is so interested on having a high resolution spectropolarimeter in space. Okay, so now the topic that is more dear to my heart, which is very metal poor massive stars. And I'm going to pull back again these schematics of the evolution of the universe. And but now I would like to bring your attention to the arrow of metallicity. So metallicity in the universe has increased from 0 after Big Bang nucleosynthesis to roughly a solar metallicity composition of today. So this means that if we want to understand the role of feedback of massive stars in early stages of the evolution of the universe, we need to understand these objects with a very metal poor metallicity. If possible, way poorer metallicity than the content of the small Magellanic Cloud. So at the moment, I think in the Magellanic Clouds, we are in decent shape, thanks to past surveys like Flames and Ulysses, and thanks to future surveys like Foremost. But this is not the case for metal poor massive stars. And that's why a bunch of us is working on this metallicity ladder. This metallicity ladder means that we are trying to study massive stars in environments of ever decreasing metal content that eventually they would allow us to extrapolate to the physical properties of massive stars with zero metallicity. I know this is a long if, but maybe in the future. And here I would like to highlight Sextans A, where we have been doing a lot of work. Leo A is not here, but it has basically the same chemical composition of SACTIC. And also, I would like to highlight 1Twiki18, which at the moment is kind of like the holy grail because it has the lowest oxygen abundance in nearby galaxies that we know of, and a very high star formation rate. So it's like a treasure trove of massive stars. What's the problem? that nature has it this way, that the more metal-poor galaxies are also farther away. And 128, for instance, is located at 20 megaparsecs. How do we study these very metal-poor massive stars? Sorry. We really need the largest telescope in the world. So there are some pioneering works with the BLT and Force 2 by the Hawaii team. And but I think at the moment, the most efficient way to study these stars is with large field integral field unit spectral apps like MUSE and KCWI. But of course, the field of view of this IFU is okay, but it's not optimal. And at some point, we need to migrate to wider field of view spectrographs like Osiris at the GTC and other possibilities at Keck and MMT. There aren't many very metal-poor massive stars known at the moment. The largest one is this catalog by Marta Lorenzo, where we listed about 150 orbital stars in sextances with a metallicity of 1/10 solar metallicity. And if we want to study the properties of these stars in an HR diagram, which is what I show here on the right, you will agree with me that this is really insufficient to say anything about the evolution of these stars. We just don't have enough information. So we need more information. Okay, so ideally, what would we need? We would need to carry out first a census, if possible with IFUs, so we are complete and we are not biased by selecting the targets. Sorry. A subsample of them, the best one or the most interesting ones or the ones that are simply brighter would be studied probably with follow-up spectroscopy, so we can get better signal-to-noise ratio spectra. And then we would study the winds of a subsample of the subsample, because ultraviolet is very hard. Getting Hubble Space Telescope is hard, but also extinction kills you. So 0.5 magnitudes in the optical range, it's not so bad. If you go to the ultraviolet, it could mean that your star is no longer detectable. Okay, so for the census, which would result in a spectral classification, we don't need so high spectral resolution. Resolution of 1000 is okay, and signal-to-noise ratio of 50 or even lower. And if and with this, we would get of the order of hundreds of thousands of the stars, or thousands of stars, ideally, because then this depends on the star formation rate of the galaxy we are targeting. But this would be the ideal case. And then we will need to determine effective temperature and gravity. And for that, I think the wide field spectroscopic telescope and blue MUSE are going to be fundamental. I think they are going to increase really the census of massive stars. And for some of them, if the signal-to-noise ratio is high enough, we will be able to determine the stellar parameter. But then there's if we really want to understand evolution and how the internal transport mechanism works and the role of rotation and maybe detect or not magnetic fields, we really need to get the abundances. And for that, we need a spectral resolution of 5000 and very high signal-to-noise ratio. And then, of course, for the wind, the requirements in resolution and signal-to-noise ratio is not so high, but again, we need access to ultraviolet. And here, I think this is a science that will need to wait for the ELT and for Hubbles. Just very quickly, because I'm taking a lot of time, I'm gonna guide you through this plot. So here, what I have done is to take the brightest and the faintest odd-type stars according to the calibration of Fabrice and Martin, and I've put the stars at different distances. So this would be the distance of the large and the small Magellanic Cloud. This would be the distance of what I call the inner local group galaxies. So this is up to 750 kiloparsecs. Then 1.5 megaparsec, which would be what I call the outer local group. We could debate about this. And then also at the distance of 1 Twiki 18. What I show here is that thanks to the ELT, we will be able to observe massive stars comfortably out of our distance of 2 megaparsecs. Maybe we could push it a bit further to 4. So this is great news, right? Because we are going to have mosaic. With the ELT, we will have this super nice sensitivity and a nice spectral resolution to do the analysis we want. But we need to be ready, and this is why I wanted to show this. So this is sextance A, and the circle would be the field of view of mosaic. And it's like, fine, the galaxy fits with the mosaic. So again, Miriam, this is good news. Yes. But then we don't have continuous coverage. We don't have a spectrum of each spaxel as we would have for an IFU. With mosaic, we will have a fiber bundle within each of these circles. And the patrol area can exceed a little bit the circle. But anyway, we need to count that we will have 1 star per circle. And in other words, this means that we cannot use the ELT to find massive stars in these metal poor environments. We need to be ready, and we need to do this work now. And the other thing I wanted to highlight is that the mosaic is not going to be assisted by adaptive optics. So we will have situations like this one, where we will need adaptive optics to see really what's going on inside this bubble. But that's not going to happen with the ELT or with any ground-based telescope, because it's very difficult to make adaptive optics work in the optical range and over a wide field of view. And I think this is where hub worlds, again, could make a difference. But the problem is, at the moment, there are no plans to have an optical range spectrograph on board the observatory. One possibility is to try to extend the coverage of LUMOS to the optical range, but for sure we will need to work to rally for this, to try to get this into the technical specifications. And well, and of course, hub worlds will be fundamental to study the winds of these very metal poor massive stars. So here I have played a similar game. I've taken the ultraviolet flags of OB-type stars in IC 1613, and I've taken them to sextance A and to further and further galaxies. And hub worlds, which is equivalent to LUGOR B, will be able, extinction permitting, to study these OB-type stars all the way to 4 megaparsecs. And of course, it would be great to have multiplexing, because now for some stars, we need to spend 9 orbits of Hubble Space Telescope on one target. Imagine if we could do several of them. So for sure, these multiplexing capabilities in the ultraviolet are going to be amazing. Okay, the last topic I'm going to touch on, this is going to be very quick, is very massive stars. At the moment, the most massive resolved stars we know to date are 136, A1, and A2, which are at the LMC, at the core of the Tarantula Nebula. And we still don't know for sure how massive the stars really are. And this is because they are not well resolved, even with the highest spatial resolution capabilities we have to date, which are the NUV camera on board STs. And this is basically what I show here, that different works obtain different results. And the reason besides the differences in the methodology of analysis, is that the data are not good enough. But this is a problem we need to answer. We need to know if there is an upper mass limit, and we need to know if this upper mass limit depends on metallicity. And the reason is the following. The general hypothesis is that in the absence of metals that can cool down the cloud where the star forms, it means that the cloud will not fragment, will not break down so much. So in principle, you could form a more massive star. And actually, this is one of the hypotheses why some simulations show that the first star could be extremely massive. So we could test this with the metal-poor galaxies of the local group and nearby. And that's what I tried to show here, the sequence of decreasing metallicity. But the thing is that in galaxies like IC 1613 or Sextans A, we are not finding stars more massive than 60 solar masses. And of course, the reason could be that the present-day star forming rate is not very high, or that the population is a bit old, or whatever. So we will need to go to this holy grail galaxy, which is 1Zwicky-18. And just very quickly, I show here that this is a science case that both the ELT with harmony will be able to almost tackle, not totally, but they will be able to at least study individual galaxies in a compact cluster, like in a compact region like the Tarantula Nebula. And hub worlds will have a smaller diameter, but since it will work also in the ultraviolet range, and the diffraction limit also is smaller, so it will also be able to say something about this problem. And yeah, so this is what I wanted to show, that either in the outskirts of a cluster like the Tarantula, like NGC 2070 in 1Zwicky-18, or in the local group, both harmony and hub worlds will be able to say something about this problem. And this was my last slide. Since I'm out of time, I will leave you with my conclusions, and thank you very much for your time and your attention.
So Miriam, huge thanks for this very extensive summary of ongoing and future developments in terms of observing facilities, and also the question that will be driving some of our research in the next years or even decades. And I like it very much how you've been at the end making the connection between both, because I think it's very important that to understand what facilities we will have available to do some of the science we want to do. If not, you can have an idea, but if the observations are not able to be done, then we are done. So I think this will
or
be
you can design your own instrument.
Design effectively. Yeah. So I hope this, in addition to people here, since this will be also on YouTube, will be very interesting for the new generations to know, to settle the basement for the future. So now it's time open for questions. So please raise your hand whenever you want to ask something to Miriam. Any question there? If not, I can start with one. You've been talking about this Habitable Worlds Observatory. So it's already in the name that is clear what is the main purpose of this mission. So what is your impression after interacting with the scientific community? There will be room to still get observations of massive stars if we have the appropriate instruments, or at the end would be facility that will go mostly to this planet search or research, and it will be only a few time to fight to get us observations for us?
I cannot answer that because yeah, I suppose there will be a time allocation committee as there is now, and usually what happens is that the observing time is granted according to the pressure on each of the sub-panels. But really, I don't know. What I can say is that the scientific working groups that are assembling at the moment are not only for exoplanets. So for instance, I think AIDA is also connected as well. We are in one that is called the origin of the elements, and we are the subgroup of resolved stellar populations, I think. So we are a sub-working group within another sub-working group that tackles this very wide problem. So I think science on any other topic that is not planets is guaranteed. Okay. But the good thing is that the Academy of Sciences found the topic interesting enough as to build the observatory, and we need to be thankful because they are driving the requirement of the diameter, and otherwise we may end up with a smaller telescope that of course we will make do with whatever we have in the end, but in this case I really think
important to make noise and be active in all these subgroups to
yeah. So some of you may hear from me at some point, because right now we only have like a steering committee, and of course we are not experts on everything, so we may reach to different people for help.
Okay, we have here one question by Ilek in the chat, so maybe you can ask yourself directly.
Hey, can you hear me?
Yes.
Cool. Thank you very much for this great talk, Miriam. And my question was concerning the magnetic fields of stars which have been measured. Have they been measured mostly in main sequence stars, or do we have any insight about what the magnetic field look like for more evolved stages like giant or blue supergiants?
Yeah, so for this, I will send you to the experts on magnetic fields. Unfortunately, the only thing I can tell you is that I think mines and Bob's mostly targeted main sequence stars. Well, Sergio, maybe you know about this, and maybe some blue supergiants.
Yeah, but I think it's more tricky to get the proper observations for those. I'm also not really expert, but yeah, this is more limited.
Yeah, and of course, this is a very interesting thing, because we need to know how the fossil field evolves and what happens at the end of the evolution of the star. But as far as I know, there are only very few results. But more than that, I would tell you to talk to Greg Wade or Veronique Petit or Sol Caselsi, who really know much more than myself on this topic. So sorry that I cannot be more specific on the answer.
Oh, thank you very much. Thanks.
Yo.
Yeah. Thank you, Miriam, for this very excellent talk and for this very nice perspective what to do in the next 20 or 30 years. So I guess we will have still some work to do. I want to respond here and comment a bit on one point of your conclusions, namely what you write here in the second but last point is a detailed description of the evolution and winds of very metal poor massive stars and blah, blah, blah. So the winds of very metal poor stars, this is something which also deserves some comments. And as you know, and maybe that's also here for the others, the dependence of mass loss rate on metallicity, at least the predicted one, is not a really monotonic one. Yeah. Because since the majority of the acceleration goes to the metal ions, and the metal ions transfer then their momentum to the bulk material, which is hydrogen and helium, via Coulomb collisions. So via collisions, it should be clear that from a certain critical density on, there might be certain problems, namely that you simply then shoot out these metal ions out of the atmosphere, and there will be no longer wind, simply because there would be no longer any coupling with the bulk matter. And this is something which has been investigated in the 2000s, around the year 2000s, plus minus 4 years, and earlier but not later. And this is something which nowadays, particularly when we look in these very metal-poor environments, should be reconsidered again. There are a lot of very interesting but also difficult theoretical questions. And currently, we do not know whether metal line driving is actually able to work at metallicity, say, below 1/30 or something like this. So this is one of the questions which also needs to be answered by these kinds of observations. Thanks.
Thank you. Thank you. Oh, yeah, I will try to be more specific about this in the future. Thanks for the remark. There is also, I think it's Norbert Pritzvila who pointed out that I said that the spectrograph on Mikado will have a resolution of 2000. That was a mistake. The spectrograph in Mikado at the ELT will have resolution of 20,000. So sorry about that.
Good. Any other question here for Miriam? If not, you know that the way is always open to ask questions offline, and I hope you find it very interesting, this talk. And see you soon. And once more, Miriam, thank you very much for accepting the invitation, and also the preparation of all this talk that I can imagine that is has been a lot of time.
Thanks for the things. Yeah, and please, anybody email me if you want to discuss something else. Yeah.
Good. Ciao, ciao.
Thank you.